I'm going to show you 3 equations and have a little rant about how double standard math is. This first equation, we can cancel a 4 and the equation's still true. Second equation, well, you can't cancel the 0 because 6 is not equal to 3. So you can't cancel zeros. That's nothing new. The third equation, though, we kind of can cancel 0 and the equation's still true. So, I mean, what gives? Maybe the simple answer would be you can't cancel 0 with some exceptions, but like what makes 0 an uncancelable integer? And the truth is 0 isn't the only integer that we can't cancel if we introduce a modulus to our integers. In other words, if we're dealing with the integers modulo z. So let's extend our arithmetic to not just the integers, but the integers modulo z. We can introduce this uncancelable term. I'm gonna struggle saying that one. Uncancelable term. I'm gonna call it. Let me define it first. So I'm gonna introduce some a mod n in the integers mod n. I'm gonna say a mod n times b mod n is equal to 0 mod n. Here's the catch. B mod n isn't 0. So we're taking something times something non-zero gives us 0 back. I'm going to call a mod n a divisor of 0 or 0 divisor. And although this is the fancy name that many textbooks give this a mod n, this is really the same thing as our magical uncancelable term. That's right. These 0 divisors, I'm going to show you an example of a non-zero uncancelable non-zero term in just a second, but these divisors of 0 behave very similar to 0 in the sense that we're not allowed to cancel them. Okay, so let's introduce a modulus to our integers. So instead of just dealing with the integers, I'm going to say the integers modulo 12. That's like adding along a clock, right? For example, 4 mod 12 times 0 mod 12, what's that? Well, that's just 0 mod 12. Which means that by our definition of a 0 divisor, 0 itself, or I say mod 12, but really with any modulus in, 0 itself is a 0 divisor. And that makes sense because we couldn't divide by 0. I'm going to claim soon that you can't divide by any 0 divisor. So you can't divide by 0, but I'll show you exactly why that's the case. Moreover, what's 4 mod 12 times 3 mod 12? Multiply 3 mod 12 4 times. So in other words, move around your clock 12 times. So that's 3, 6, 9, 12. By multiplying by 4, this thing vanishes. We go back to 12 mod 12, which is 1 mod 12. Therefore, we have 2 more 0 divisors, modulo 12. We have 3 mod 12 and 4 mod 12. So 0 is not the only uncancelable term. We also have 3 mod 12, 4 mod 12. Actually, there are infinitely many terms in general, not just with integers modulo 12, but with modular arithmetic, we can come up with infinite number of these uncancelable terms. So let me explain exactly what makes them so tricky when it comes to canceling. So let's give ourselves the general case where we want to cancel a term a mod n. So here's our equation, and ideally I want to be able to cancel this a mod n. What I'm going to do is try and rewrite this in a way that looks a bit more familiar to our definition of a 0 divisor. You'll see why in just a second. I'm going to subtract the right hand side to get 0 on the right hand, 0 modulo n. And then I can factor out this a mod n. So I get a mod n times some term is 0 mod n. This is really similar to our definition of a 0 divisor. So I first claim that if a mod n is not a 0 divisor, we can in fact cancel it. There's 0 ambiguity and everything will work out. So let's say it's not a 0 divisor. By the way, if it's not a 0 divisor, then it itself cannot equal 0. This isn't equal to 0 modulo n. And the only way that we could get this product here to vanish to 0 is if in the second term in our product we're equal to 0. This green term has to be 0. Otherwise, there's no other way this product could get to 0. If b mod n minus c mod n is equal to 0 mod n, then immediately we have b mod n is equal to c mod n. Compare that to our very first equation, and voila. What happened was we canceled the a mod n. If a mod n is not a zero divisor, we're allowed to cancel, and you can skip all these steps. You get to a perfectly disambiguous case. All right, let's try and deal with that uncancelable monster. Let's say a mod n is a zero divisor. Well, what does that entail? Let me remind you with this clock right here. We had that 4 mod 12 times 0 mod 12 is 0 mod 12. But we also had that 4 mod 12 times 3 mod 12 is 0 mod 12. And let me really emphasize that neither 3 mod 12 nor 4 mod 12 are 0. But multiplying these two non-zero things give us 0. That's the power of the zero divisor, that it can take two non-zero things and turn it into something 0. But the problem is there's this ambiguity, right? So what can we say about this second term? It could be in fact 0, just like in this first example. If the second term were equal to 0, then this would definitely still be true. But we also saw an example where the second term in our product might not be 0. So this term may or may not be 0. There's simply not enough information to know. In other words, there's not enough information to know if b mod n is equal to c mod n. And again, if you compare that to our first equation, what this is really saying is if a mod n is a zero divisor, then it's too ambiguous to cancel a mod n. If the term isn't a zero divisor, then we can always cancel them without the fear of ambiguity. However, if the term is in fact a zero divisor, this is the catch. We can sometimes cancel it because there's this ambiguity.